In materials that exhibit antiferromagnetism, the magnetic moments of atoms or molecules, usually related to the spins of electrons, align in a regular pattern with neighboring spins pointing in opposite directions. This is, like ferromagnetism and ferrimagnetism, a manifestation of ordered magnetism. Generally, antiferromagnetic order may exist at sufficiently low temperatures, vanishing at and above a certain temperature, the Néel L temperature. Above the Néel L temperature, the material is typically paramagnetic. Measurement: when no external field is applied, the antiferromagnetic structure corresponds to a vanishing total magnetization. In an external magnetic field, a kind of ferromagnetic behavior may be displayed in the antiferromagnetic phase, with the absolute value of one of the sublattice magnetizations differing from that of the other sublattice, resulting in a non-zero net magnetization. Although the net magnetization should be zero at a temperature of absolute zero, the effect of spin canting often causes a small net magnetization to develop, as seen for example in hematite. The magnetic susceptibility of an antiferromagnetic material typically shows a maximum at the Néel L temperature. In contrast, at the transition between the ferromagnetic to the paramagnetic phases, the susceptibility will diverge. In the antiferromagnetic case, a divergence is observed in the staggered susceptibility. Various microscopic interactions between the magnetic moments or spins may lead to antiferromagnetic structures. In the simplest case, one may consider an Ising model on an bipartite lattice, for example the simple cubic lattice, with couplings between spins at nearest neighbor sites. Depending on the sign of that interaction, ferromagnetic or antiferromagnetic order will result. Geometrical frustration or competing ferro and antiferromagnetic interactions may lead to different and, perhaps, more complicated magnetic structures. Antiferromagnetic materials: antiferromagnetic materials occur commonly among transition metal compounds, especially oxides. Examples include hematite, metals such as chromium, alloys such as iron manganese, and oxides such as nickel oxide. There are also numerous examples among high nuclearity metal clusters. Organic molecules can also exhibit antiferromagnetic coupling under rare circumstances, as seen in radicals such as 5-dihydroxyxylylene. Antiferromagnets can couple to ferromagnets, for instance, through a mechanism known as exchange bias, in which the ferromagnetic film is either grown upon the antiferromagnet or annealed in an aligning magnetic field, causing the surface atoms of the ferromagnet to align with the surface atoms of the antiferromagnet. This provides the ability to pin the orientation of a ferromagnetic film, which provides one of the main uses in so-called spin valves, which are the basis of magnetic sensors including modern hard drive read heads. The temperature at or above which an antiferromagnetic layer loses its ability to pin the magnetization direction of an adjacent ferromagnetic layer is called the blocking temperature of that layer and is usually lower than the Néel L temperature. Geometric frustration. Unlike ferromagnetism, antiferromagnetic interactions can lead to multiple optimal states. In one dimension, the antiferromagnetic ground state is an alternating series of spins, up, down, etc. Yet in two dimensions, multiple ground states can occur. Consider an equilateral triangle with three spins, one on each vertex. If each spin can take on only two values, there are 23 equals 8 possible states of the system, 6 of which are ground states. The two situations which are not ground states are when all three spins are up or are all down. In any of the other 6 states, there will be 2 favorable interactions and 1 unfavorable one. This illustrates frustration, the inability of the system to find a single ground state. This type of magnetic behavior has been found in minerals that have a crystal stacking structure such as a kigome lattice or hexagonal lattice. Other properties: synthetic antiferromagnets are artificial antiferromagnets consisting of 2 or more thin ferromagnetic layers separated by a non-magnetic layer. Due to dipole coupling of the ferromagnetic layers results in antiparallel alignment of the magnetization of the ferromagnets. Antiferromagnetism plays a crucial role in giant magnetoresistance, as had been discovered in 1988 by the Nobel Prize winners Albert Fert and Peter Gra 1/4 NBERG using synthetic antiferromagnets. There are also examples of disordered materials that become antiferromagnetic below their NA copyright L temperature. These disordered networks frustrate the antiparallelism of adjacent spins. That is, it is not possible to construct a network where each spin is surrounded by opposite neighbor spins. It can only be determined that the average correlation of neighbor spins is antiferromagnetic. This type of magnetism is sometimes called Spur Magnetism. See also. References. External links: Magnetism, Models and Mechanisms in Epavrani, E. Koch, and U. Skolwa. Paragraph CK, Emergent Phenomena in Correlated Matter, JA 1/4 Lic 2013, ISBN 978-3-89336-884-6.